Okay, so this next question I actually thought was going to be the most challenging question for you guys, but this is actually the one that you did the best in, so I just want to say really well done. First of all, acceleration is proportional to the displacement in the negative direction. That was our conditions of simple harmonic motion. So you got 1 mark for saying acceleration is proportional to displacement, or you could have had the second mark for saying in the opposite direction, or saying that acceleration is directed towards the equilibrium position. Okay, so it's 2 marks up there for saying those ones. The next part then, we were looking at something undergoing simple harmonic motion, and it was a mass on a spring, okay? And we were told that we have a 52 kilogram mass, and it's going through SHM with a period, so a time period of 0.86 seconds when attached to the spring. We then attached it to the same spring, oscillating though with a period of this. It's asking us then to calculate the mass of the new wooden block. So we go to using our time period equation. Now, I actually did a ratio here. You could do this in different ways. Some people did this and found out K and then substituted K in to the next equation. But essentially, you could also work out that time period squared is proportional to the mass. Okay, and the time period squared is again proportional to the second mass. So I just did a ratio for this in here. So I said this, the time period of the first one was 0.86, so 0.86 squared, and that was equal to 0.52. And then I did the time period squared for the second one, which was 0.74 squared, and then I didn't know the mass for this, so then I just rearranged, so brought my mass up, brought these down, and got 0.39. But this one was answered really well, guys. Some people did this a little bit differently. They found out K, so they said like T squared was divided by 4 pi squared was equal to m over k. They then found k, and then they put it back in up here. That was another way you could have done it. I just quite like doing the ratios, so I didn't have to worry about k and 2 pi, and you just got rid of them straight away. 19C. In carrying out the experiment, the student displaced the block horizontally by 4.8 centimetres. Remember, centimetres is 10 to the minus 2. It says determine the total energy of the oscillation. So most people did really well again on this question. We got the total energy coming up to be in the equation half m omega squared x naught squared. And a lot of you found out your angular frequency by using 2 pi divided by 2, so 2 pi divided by 0.74 to get 8.5 radians. Okay, essentially then we got a mark for putting in our working, so we had 0.39 for our mass. So using your answer from previous that you got for part B, our angular frequency, and then our 4 times 10 to the minus 2 squared, and that gave me 0.032 joules for the final mark there. Again, the next one, I also thought you guys would find this one really tricky, so I was really impressed that you guys did really well with this. Essentially, when we're having 2 springs in parallel, we're increasing the spring constant because each of these springs has one of K, so we're having to pull against both of them, so we're increasing the spring constant here. Okay, again, using the equation, T is equal to 2 pi root m over K, we can see that T squared is proportional to 1 over K, or inversely proportional, sorry, to K. So essentially, if we've increased K, we're decreasing the time period. All right. Now, if we're decreasing the time period, that means the fractional uncertainty of the time period is going to increase, because if this becomes a smaller value, this whole thing then becomes a larger value. Now, essentially, again, because of this relationship here, we know that T and M are related through this fractional uncertainty that we've got going on, sorry, this division that we've got going on here. So in this case, like T squared is proportional to M. So in this case, if my T squared is increasing, okay, so my fractional uncertainty for T squared is increasing, my fractional uncertainty for M is also increasing. So most people did really well on that for 3 marks. So you got a mark, the spring constant, a mark for saying that the time's going to decrease, and then this sort of idea here that the fractional uncertainties are going to increase was your 3rd and final mark for those. The next one, most people I think got this one correct. I think there's only maybe 1 or 2 that didn't. Essentially, if the wave is moving this way at P, which is currently at the rest position, the next part of the wave moving along is to the left. So P is going to move to the left. All right, so you've got a mark for saying to the left. And then the last one was about whether it was a compression or a rarefaction. So if I just hold this down here, you've got a mark for recognizing it's the center of the rarefaction. Be really careful with your language then, because it says explain. So I had a couple of people saying, oh, it's on the positive gradient. That was just me showing you and trying to use the language to describe to you about compressions and rarefactions. You have to explain it, all right? So in this case, I look at the particles on either side of them. Particles to the right are moving to the right, so they are moving away. Particles to the left are also moving to the left. They are also moving away. All right, they're both moving away. They are spreading out, which means it is a rarefaction. Okay, so center of the rarefaction and a mark for describing that both particles on either side are moving in opposite directions. Okay, so if they're moving in opposite directions away from the particle P, that's why we get a rarefaction in there.